edition of the Ken Seminar Series during this 2025. Today it is the pleasure of ICT to introduce Professor Giorgio Rizzoni. Giorgio Rizzoni is the Ford Motor Company Chair in Electromechanical Systems at The Ohio State University, where he directs the Center for Automotive Research and is a professor of mechanical and aerospace engineering and electrical and computer engineering. He earned his bachelor's, master's, and his PhD degrees in electrical and computer engineering from the University of Michigan. His research is currently focusing on advanced propulsion systems modeling and control, vehicle diagnostics and prognostics, electrified powertrains, energy storage systems, autonomy and sustainable mobility, and his work informs the development of cleaner, safer, and more efficient transportation technologies for the next generation of vehicles. With that said, please help me give a warm welcome to Professor Giorgio Rizzoni today to our seminar.
Thank you very much for the kind introduction. Thank you. It is really a pleasure and a great honor to have been invited to the Kent Seminar Series. The last time I visited the University of Illinois was, I think last spring. There was a National Academy of Engineering meeting, and I had the pleasure of participating in a very interesting workshop on the subject of electrification of transportation. So it's great to be back virtually. I wish I could be there in person. And I understand that this is an audience that has experience and activities related to transportation. Think of the things we do as being more related to the actual vehicles that are part of the larger transportation systems. So perhaps my presentation today might be a little bit different in flavor from the things that you're used to listening to, and I hope you'll find it interesting. I'll talk about, in a broad sense, about some of the motivations for the changes that are taking place at a very rapid pace in the field of transportation. I'll start with a couple of words about who we are, what we do. You see that I serve as the director of the Center for Automotive Research at The Ohio State University. We're an interdisciplinary research center. We have our own home on the West Campus of The Ohio State University. We are a pretty sizable research organization, about give or take a $20 million a year research enterprise. We do work funded by government agencies and private companies, mostly the automotive industry. I'll say a couple of words about our population of students, the most important part of our operation. We have over 120 student employees here. Most of them are graduate research associates, but we also have a substantial cohort of undergraduate research assistants. They're the next generation we hope will enter the graduate ranks in the future. So pretty sizable organization, many professors participating in our activities. It's an interdisciplinary research center, so we have collaborators from mechanical, aerospace, civil, electrical engineering, computer science, material science, and we do research in many different areas. I'm going to talk about electrification today, and I'll take just a couple of minutes to give you a little bit of background. I started working on electric vehicles in 1994 when we raced an electric car. You can see it here in the top left corner of this slide, in open wheel, single-seater kind of race car that raced in the second half of the 1990s in a competition that was called Formula Lightning, a precursor of what today is Formula E. We went on to translate this know-how in electric vehicles to a series of vehicles that over the years set a number of records, land speed records, from the original Buckeye Bullet that set a record for US land speed. It was the first electric car to go over 300 miles per hour. The second generation vehicle set a record that is still holding. It's a FIA record at over 300 miles per hour for a hydrogen fuel cell car. We moved on from there to vehicles that are powered by lithium batteries, and the Venturi Buckeye Bullet 3 in 2016 set what is today still the FIA land speed record for electric vehicles at over 340 miles per hour, which is pretty crazy if you think about it. There are airplanes that fly at lower speeds than that. So I just wanted to establish the fact that I've been working on electrically powered vehicle for a very long time, over 30 years. And over the course of this time, there have been many collaborations with the automotive industry, funding from the US Department of Energy. We've worked on many, many different programs. So what I'm going to do, I forgot about this last detail. More recently, in the summer of 24, we set an FIM land speed record with an electric motorcycle. That's a 150 kilogram electric motorcycle that went over 180 miles per hour on the Bonneville Salt Flats. So I'm going to try to give you the big picture. Why is it that the topic of electrification is important, and how might this develop to change the way in which we move people and freight goods? So it's clear that mobility is a very important part of our society. We spend significant amount of energy and effort to move people and to move goods. And the automotive industry has been the inspiration for many great transformations in our society. I take as an example the Henry Ford concept of a moving assembly line, which today is the way most goods are manufactured. But the first instance of a moving assembly line was something that Henry Ford demonstrated in 1914, reducing the production time for an automobile from half a day to about an hour and a half. Pretty amazing development. Electric vehicles, back then in 1914, were actually not a new idea. First electric vehicles were demonstrated in the late 1880s. You see here some drawings. I'll show you some photographs in a moment, but you see some drawings here of the two earliest electric vehicles. And if you look at the one on the right-hand side, you can see that the tray of batteries on the bottom of that tricycle looks an awful lot like the lead acid batteries that serve as starter batteries in conventional automobiles today. Some of this technology has not changed that much over the years. Electric vehicles moved on and were quite successful for a number of years. When you look at the early 1900s, the first 2 decades of the 1900s, it was probably just as common to come across an electric vehicle on the road as it was to see an internal combustion engine powered vehicle. Here are some companies that lived probably for the span of at least a couple of decades. Baker Electric in Cleveland, Ohio, Detroit Electric, of course. And here is a picture of the Columbus Electric, based here in Columbus, Ohio, where I live. Actually, it turns out the address of this company, 561 Dublin Avenue, is not very far at all from where I live today. So in the early 1900s, electric vehicles were quite common. What happened? How did they disappear? Well, first of all, if you look at statistics from 1913, you could buy a gasoline engine automobile for about $1,000, maybe even less than $1,000. Whereas an electric car would run in price somewhere in the neighborhood of $2,000 to $3,000. So it costs 2 to 3 times as much. But at the time, electric vehicles were far more reliable and easier to operate. I don't know how many of you have ever operated a hand crank start for a combustion engine, but until the invention of the electric starter, operating an internal combustion engine powered car could be a bit of an adventure. They were also not very reliable. But what happened was that in the 19 teens, technology related to internal combustion engine, their reliability and their efficiency, and the availability and distribution of liquid fuels, gasoline, liquid hydrocarbon fuels, improved to the point that for the next many decades, internal combustion engine power vehicles really dominated the market, and they were the more affordable, reliable, and effective means of transportation. So this is a little bit of the history, and of course you know that over 100 years later, today you can buy a battery electric vehicle, you can buy a hybrid electric vehicle. There are many different options available to you on the market, but for many decades, the gasoline-fueled internal combustion engine was the dominant force. Let me change topic now to the subject of energy. Transportation, as you will see in a moment, is the single largest sector of our economy in its energy usage. And if you think about it, to provide the propulsion power that is needed for a vehicle, on one hand, you need a propulsion system of some kind, but you also need to store energy on board the vehicle. And in the world of the early 1900s, late 1800s, engineers understood the steam engine. There were, by the way, in the early 1900s, steam engine powered cars as well. They were not as successful as the internal combustion engine and electrically driven cars, but they existed. The internal combustion engine has been around since the late 1800s, electric motors even longer than that. And the energy storage technologies that exist today and existed also at the turn of the previous century were either liquid fuels for the combustion engines or electrochemical batteries. Both of these technologies have also been around for quite some time. Batteries were initially discovered at the beginning of the 19th century, actually. So what is this energy storage or fuel for transportation? What characteristics are we interested in? Well, we need two things in an energy storage system for transportation. We need to have the ability to store energy, and that is related to the range of the vehicles. You fill up your tank. My car has probably about a range of 500 miles on gasoline. A battery electric vehicle today, they're advertised as having a range of 300 miles. But you're also interested in power density, which is related to performance, the ability to transform the stored energy into power that can deliver motion. So it's worth spending a minute on understanding the significance of energy consumption in the United States. If you go back and look at the history of energy in this country, and any industrialized country would have similar evolution. In 1776, everything we did was based on a single sustainable biofuel known as wood. We used it for heating, for cooking. There wasn't much use of energy for transportation other than that available from wind or from animals, horses or oxen. In the 1800s, we went through this industrial revolution, and coal became a far more attractive material for providing energy storage and for converting this energy into power. So steam-powered ships, trains, and other industrial facilities could take advantage of coal, and this led to what we think of as the Industrial Revolution. But if you see what happens here, at some point in the early 1900s, petroleum and associated with it natural gas came to be a very important part of the energy supply for industrial applications, but especially for transportation. Today, we live in a world in which fossil fuels, petroleum, natural gas, and to a decreasing extent coal, represent close to 80% of the total energy supply in the United States, and non-fossil fuels represent about 20%. And a big part of this in the United States is nuclear power. Then you have all of the different renewable energy sources. I'll show you a snapshot of the same information in percentage instead of absolute units to make the point that we went from the wood age to the coal age to the petroleum age. And today we are still in the petroleum age. I'll show you some numbers that illustrate this more clearly in a moment. So if petroleum has fueled transportation for 100 years, but we would like to move away from fossil fuels, from these liquid hydrocarbons that produce carbon dioxide emissions. What is our alternative option? Well, there certainly has been a lot of talk about electricity as an alternative to petroleum-based transportation. And so at this point, I think it's appropriate to take a look at some historical and then current data on energy usage in the United States. This diagram is very powerful to understand where we were about 20 years ago. I'll show you data from 2003 and then from 2022. On the left-hand side, in this different color coding here, you have all of the primary energy sources that we use: petroleum, coal, natural gas, biomass, geothermal, wind, hydroelectric, nuclear, solar. These are the primary energy sources that end up feeding four major sectors: residential, commercial, industrial, and transportation. Transportation, as you can see, is the largest energy consumer in the US economy. And again, this would be true in any industrialized economy. And when you look at what feeds transportation, well, it turns out that most of it, 97% approximately, in 2003 was petroleum. Industrial applications made use of many different sources of energy: electricity, natural gas, coal, biomass, and petroleum as well. But an important segment, an intermediate segment between primary energy sources and end uses, is electricity generation. And a little more than 20 years ago, when you look at electricity generation, 20 out of 38 units, so more than 50% of the electric power, was generated by burning coal. Natural gas gave us another substantial portion. Nuclear power was the second largest provider of primary energy for electricity generation, and hydroelectric power was the next one. So back in 2003, electricity production was very strongly dependent on fossil fuels, 25 out of 38 units. And what are these units? Well, 98.1 quads. Quads is an abbreviation for quadrillion BTUs, British thermal units. And to have a round number, the United States for the past few decades has used approximately 100 quadrillion BTUs annually, huge amount of energy. So let's take a leap forward by 20 years. And if I look at the data for 22, and by the way, these charts from Lawrence Livermore National Lab are very easily accessible. You can just look it up and find them easily. In 22, still almost exactly 100 quadrillion BTUs. What do we see on the right-hand side? That residential, commercial, industrial, and transportation still represent approximately the same fraction of total energy usage. What we see now is that in 20 years later, transportation was somewhat less dependent, from 97% to 89% dependent on petroleum. What replaced that petroleum that was used 20 years before for transportation? Well, primarily two things: biomass and natural gas. In 22, the fraction of electric power that was responsible for transportation was still really microscopic. But when you look at electric power generation, you see a dramatic difference in the rainbow of colors that are related to electricity generation. 20 years before, solar power was practically insignificant. A few years ago, true today as well, solar power is close to 2% of the total energy supply for our country. Wind power, again, was a very small number, probably less than 1% in 20 years earlier. Today, wind power is approaching 4% of the total. Hydroelectric has remained about constant. Nuclear has remained about constant. But what has changed in a significant way is that electricity generation is now much less dependent on coal-fired power plants. You can see here that coal has gone from being more than 50% to probably a little less than 25% of the total. Some of the energy provided by coal has been replaced by natural gas. Well, natural gas is still a fossil fuel, but its carbon intensity is much lower than that of coal. Wind now is a significant component of energy production naturally. And as I said, solar has also become a significant part. So the story here is that over the span of the last 20 years, we have done a pretty good job of reducing the carbon emissions in electricity generation, but fossil fuels are still responsible for about 50% of electric power generation in the US. If you look at the numbers in 22, natural gas, in fact, I say 50%, it's more like 60%. Natural gas is about 40% of the total, coal about 20% of electric power generation, nuclear a little less than that, and renewables a little more than 20%. So this is where we are today in electric power generation. We still have a long ways to go, and we still rely in a pretty significant way on coal-fired and especially natural gas-fired power. Here is another look at the same information over the time span from 1950 to 2022, where you can see that natural gas has grown significantly, coal has been reduced significantly, nuclear has been pretty steady over the last 30 years or so, renewables have been increasing, but this increase, again, represents only a fraction of the total. So even though renewable energy production is increasing at a reasonable pace, it's still representing only about a fifth of the total energy production in the United States, which means that the day when we can think of electric vehicles as being completely disconnected from fossil fuels is not here yet. We're making progress in that direction, but we're not here yet. So I have a couple of snapshots, and this is something that you can explore yourselves. There is an app, a website called electricitymaps.com. So think of the color coding in this picture of the world as follows. Green represents very low carbon intensity. Brown, the darker it is, the more carbon intensity. So you have, for example, countries like Norway, Norway and Sweden, where electric power generation, practically speaking, no longer makes use of fossil fuels. Between nuclear, hydroelectric, and renewable energy, they have replaced fossil fuels completely, to countries like India, for example, Mongolia, where on the other hand, there is still a very, very strong dependence on coal power generation. The same is true for Australia as well. So let's take a closer look at our country. And here in the United States, you can see that as you look at different parts of the country, and by the way, this data changes from day to day. These are snapshots on a specific day, and you can see the carbon intensity scale here, where it goes from 0 to maybe as much as 1,500 grams of CO2 equivalent per kilowatt hour of electricity produced. So here you are in Illinois, and here I am in central Ohio. We're not too far. It's about a 4-hour drive. And we are in, roughly speaking, in the same position. We are beige states. We're somewhere in between here. Not too bad, not as good as we would like to be. And what is important to understand here is what are, and I picked my region, PJM Interconnection is the distribution, is the nonprofit company that is responsible for electricity transmission in our region. Illinois falls within MISO, an adjacent region. ISO stands for Independent System Operators. These are nonprofit organizations that manage the buying and selling of electric power, right? And if you look at the region that comprises Ohio, West Virginia, Pennsylvania, and parts of the East Coast, you'll see that nuclear, natural gas, and coal, and with a growing percentage of wind, represent the overwhelming majority of electric power generation. So why is this important? You may have at dinner time conversations with your friends and family, someone may have asked you, hey, you're an engineer, you work in transportation. Tell me, is it really true that electric vehicles are zero emissions? And the correct answer to this question is the answer that I always recommend my student use as a first defense, which is, it depends. It depends on where you live. It depends on what time of the day it is, because this map that shows you the carbon intensity of electricity production will change hour by hour during the course of the day, depending on how electricity is bought and sold. And so the answer here is that while we are certainly doing a better and better job of reducing the carbon emissions of the electric power grid still depends in most parts of the world on a substantial amount of fossil fuel production. So one of the other questions that this happens to me all the time. People know what I do for a living, and they say, oh, talk to me about emissions of electric vehicles. Is it true that electric vehicles are cleaner than gasoline engine cars? What about the emissions that are associated with the manufacturing of batteries, et cetera, et cetera? So there is an activity in engineering and science called life cycle assessment. And I borrowed here a picture from a good friend who wrote a book many, many years ago, but the principles are valid. Professor Lino Gutzell at the Swiss Federal Polytechnic in Zurich wrote this book on vehicle propulsion systems, in which he makes the point that on one hand, you begin in a vehicle with an energy converter in the powertrain of your vehicle. Well, we all understand that the internal combustion engine, spark ignited gasoline, compression ignited diesel engines, compressed natural gas engines, they have relatively low energy conversion efficiencies. On the other hand, electric machines have much higher energy conversion efficiency. You go from 20% on average over a driving cycle to something like 90%. But then you have to think about the fuel that powers these vehicles. So how much energy is spent in converting and transporting energy? So the petroleum needs to be refined and it needs to be transported and distributed to the fuel pump so that you can fill up the tank in your car. Electricity for an electric vehicle must be generated by the electric power grid. What about hydrogen fuel cells? Well, somehow you will have to produce this hydrogen. And so there are efficiencies that are associated with the energy conversion and transportation. And then you need to think about what's the energy source. Is it petroleum? Is it methane? Is it coal? Is it renewable power? Is it nuclear power? And then each of these has some equivalent CO2 emissions. So the answer as to what emissions are associated with a particular form of energy conversion for transportation is not a simple answer. You have to ask a lot of questions about where the fuel came from and how it's been utilized. This business of understanding the energy and fuel cycle and the vehicle energy consumption that leads to the tailpipe emissions. And by the way, when people say electric vehicles are zero emission vehicles, well, what they really mean is they're zero tailpipe emissions vehicle, because of course there are emissions associated with producing the electricity. But that's not the complete story, because there is energy that goes into manufacturing the vehicle, into manufacturing the components, into extracting the raw materials, and also we need to deal with the end of life, reuse, recycling, disposal. So life cycle analysis is a discipline that is quite complex, that it takes into considerations all of these different aspects. So my message is the next time someone asks you at dinner time, what about the emissions of electric vehicle, make sure you remember my suggestion. It depends is a very good starting point for the conversation. Now, there is another important element. I'll be brief here, but I do want to point out that energy density and power density are very important elements of the choice of a fuel versus another. If you've never seen them, these Ragone plots are logarithmic plots of specific energy, watt hours per kilogram, versus specific power, watts per kilogram, for different kinds of energy storage systems. And so you go from lead acid batteries, which have limited specific power and specific energy. Nickel metal hydride batteries for a period of time were a good substitute, an improvement over lead acid batteries. We're doing great things with lithium ion batteries today. Fuel cells, which means hydrogen, are yet higher in energy, especially in specific energy. But the reality is that the combination of specific energy and power that you can have in an internal combustion engine fueled by a hydrocarbon liquid fuel is unmatched by any electrochemical type energy conversion systems. This is one of the reasons why internal combustion engines are still with us. And I think they will continue to be with us for a very long time, especially in applications like aviation, where you do need very high energy density to enable an airplane to cross an ocean, for example, or long-range truck transportation, for example. So let me close this conversation, which really was a lot about energy and fuels and emissions. It was really not that much about transportation, but I'm hoping to give you kind of a big picture idea of some of the drivers for technology changes in our world of transportation. So I'll say a couple of things about energy systems of the futures. So there are some fascinating things that are happening in the world of electric power. We are moving in the direction of increasingly distributed energy systems. By that I mean that instead of having the simple system, you have a power plant sending electricity to a substation, you have a distribution system, and then you have commercial, residential, industrial applications. Now you're moving to a more distributed world in which you will have distributed energy resources, and you're going to have much more flexible distribution systems that allow us to actually broker the transfer of energy from one application to another in a much more flexible way. And energy storage is going to become a very important part of this. I will also make some comments about, remember that petroleum ends up being the single largest component of the primary energy supply. So we live in a world in which petroleum is produced in certain parts of the world. These are the supply regions. And then you have consumption of this petroleum. Where? Well, if you look at vehicle density and population density, East Asia, Europe, and North America are the largest consumers. They're the regions where there is the most demand. And there is an amazing amount of energy trading that takes place in the world today that is mostly based on fossil fuels, ships, pipelines, and let me give you a number. Today, the world consumes 100 million barrels of petroleum every day. 100 million barrels of petroleum per day. And this petroleum may be coming from the other side of the world, and it comes to us on oil carriers, right? Or it's shipped by pipeline from Canada, for example, to the United States, or from Russia to Europe. So this idea of having a system that is based on the transport of liquid fuels is part of our world. That's what we depend on. Could we imagine a global energy trading system in the future in which you will have the production of energy that uses sustainable energy carriers, not fossil fuels anymore? And I'll give you an example in a moment, but are there regions in which there is a lot of sunshine, a lot of wind? Could we make a lot of energy with renewable energy sources and somehow trade it? Well, a big challenge. This is not an easy thing to do. The demand regions are the same, the USA or North America, Asia, Europe. But now the supply regions could be different. They could be regions that have a lot of sunshine or a lot of wind. Could we imagine having the production of green molecules, that is, of liquid fuels or gaseous fuels that are not based on fossil fuels, but are produced in a renewable way? So e-fuels, I'll describe this in a moment, ammonia, e-hydrogen, that is green hydrogen, are potentially these fuels of the future that are still chemically bound in molecules that allow you to move them, especially with liquid fuels, more easily. So you could imagine shipping synthetic hydrogen made somewhere in the Sahara Desert, for example, where there is a lot of sunshine, using solar power to do electrolysis for producing hydrogen. Some people believe in ammonia. I'll admit that that's a difficult fuel to handle, but ammonia is a liquid carrier of hydrogen. Liquefied natural gas, where the natural gas is a biogas or synthetically produced from hydrogen, or methanol, which is the lightest liquid hydrocarbon, CH3OH, that can be produced. And it's liquid, so all of the liquid carriers, the oil tankers that we use today, could be carrying methanol. And so you say, wow, this is a nice dream. Could this possibly happen? Might I be able to supply a net zero carbon liquid fuel to airplanes that cross the Atlantic Ocean? Well, Siemens Energy and Porsche teamed up with the government of Chile It turns out that the southern tip of Chile, Patagonia, is the windiest part of the world. And what they've been doing there is using this wind power to produce green hydrogen from electrolysis. So you need water close to the coast. You need lots of wind to produce clean electric power and carbon capture. So imagine capturing carbon from the atmosphere, synthesizing this carbon with hydrogen that is produced by a green energy source, and synthesizing this into a liquid fuel. And methanol would be the easiest product, but methanol could be refined into a designer gasoline. So I believe that as we go forward, we will see more and more emphasis on substituting these liquid e-fuels for petroleum so that we can continue to use liquid hydrocarbon fuels in difficult applications like aviation, agriculture, construction machinery, long distance trucking, while at the same time translating a lot of the internal combustion engine powered local transportation in urban areas, small package delivery, passenger cars into electric vehicles. I think that in summary, we need engineers who are capable of doing life cycle analysis, who are capable of doing the chemical engineering and synthesis of these e-fuels and contribute to the design of an increasingly renewable energy focused electric power generation system. And with this, I hope I have left a little bit of time for questions, and I would love to hear from you at this point.
Thank you so much for your presentation. It's been really enlightening, Professor Rizzoni. So now we're going to open the floor for some questions from the audience. In case anybody wants to go ahead. Professor Hash, please go ahead.
Yeah, thank you for a very interesting presentation. Hopefully you can hear me well.
Yes, I can.
Great. So you talked about methanol as, and I'm assuming that would come from some biomass from some sustainable source in this scenario. What's I know probably very little about methanol, but what are the advantages versus ethanol? The only experience I have with methanol is that it's a little more maybe toxic and corrosive. Why that versus ethanol?
So ethanol is a perfectly viable solution. Today, we know how to make ethanol from biomass, and we do that. There is 10% ethanol in every gasoline you purchase in the United States at the pump, right? Methanol is a little bit trickier as a standalone fuel. You said correctly, it is toxic. It turns out that there was a time in the 1980s when the automotive industry looked at methanol quite seriously as an alternative fuel. That was in the wake of the first oil crisis, right? And the auto industry and the energy companies were looking at alternatives. But the methanol I am talking about here is produced not from biomass, but from the synthesis of hydrogen that is produced from a renewable energy source. I'm going to give you a different example than the Porsche Siemens one. Imagine that I'm in the middle of the Sahara Desert with the sun shining on land 12 hours a day. I can use that solar power through electrolysis. I have to get water there, so I can't go too far from the seashore. But through electrolysis, I am going to produce hydrogen that I can then synthesize into a liquid fuel by adding carbon that I extract from the atmosphere. So now, if I make this, and the simplest liquid fuel that I can make by the synthesis process is methanol. Now, this methanol I could put in a pipeline and send north to a refinery in Sicily, in the south of Italy, plenty of oil refineries there. And that methanol could then be refined into something that is essentially a synthetic gasoline. So what Porsche demonstrated was that you can produce, there are a couple of steps involved in this, but you can produce a gasoline that is actually better, cleaner than petroleum based gasoline by this process. The problem today is you're looking at a cost of maybe a couple of euro a liter for this process. It's still somewhat expensive. That's like $8, $9 a gallon. I want to say that that's about twice what we pay for petroleum-based gasoline. So volume production and the improvement in these processes hopefully will bring the price down. The reason why the production of synthetic e-fuels is an important alternative is that we have pretty much come close already to the limit of how much fuel we can produce from biomass in the United States without having adverse effects on the food supply. So yes, we're doing quite a bit with ethanol, but if you wanted to scale up to something that would become a significant fraction of 100 million barrels a day, we need to do something different. Biofuels alone will not do it.
Great, thank you.
Sure.
We're gonna take another question now from the audience. Go ahead, Akash, please.
Thank you, Professor, for the presentation. I was a little bit uncertain about one of the terms that you use in your slide 23. It's called rejected energy versus what you had as energy services.
Yeah, that's a good question. Let me go back to that slide. Excellent question. Someone is paying attention. This is a question that has plagued me before when I have given similar presentations. I'll explain why. So, first of all, rejected energy is related to energy losses. That is, the laws of thermodynamics are what they are. We cannot change them, right? So every energy conversion process leads to some losses. Let me give you an example. I make electric power from a natural gas-fired power plant. Well, the combustion process is not 100% efficient. So I put natural gas that corresponds to a certain amount of energy, megajoules per cubic meter, for example, and not all of that energy becomes electric power. Then this electric power, I have to transform it from a low voltage to medium voltage to high voltage. Well, the transformers have losses too. And so every step of the way, I lose some of the original energy. So that's the rejected energy. When you look collectively at all the losses, think about your home, okay? If you live in a home that has very poor insulation, your heating costs are much higher, but you're also using a lot more primary energy to heat your home, right? So one of the messages in this rejected energy is that improving the efficiency of everything we do is of fundamental importance, and engineers are essential to accomplish that goal. All kinds of engineer it takes to do it right. So how do we improve insulation in our homes? How do we make the design of electric machines that move pumps, for example, or fans in buildings? How do we make them more efficient so we lose less energy? Now, the second part of your question, what may have happened, is that, my goodness, you say in 20 years, we went from rejected energy being 55 out of 98 to being 67 out of 100. Are we becoming less efficient? So I actually wrote to the folks at Lawrence Livermore, because one year this number changed, and the answer was that they changed the way in which they calculate rejected energy, and without knowing all the details, it's very difficult for me to explain in a minute, how this works. So the discrepancy between these two numbers, the percentages, is due to the methods they use to calculate it. But let's say that they do a better job in 22 than they did in 2003. What this is telling us is that in the end, the overall efficiency of everything we do with the primary energy sources we use to do residential, commercial, industrial, and transportation functions is really only about 33%, 1/3. So 2/3 of the energy that is available at the source is, guess what? It becomes heat, right? So we are essentially increasing the entropy of the universe by converting energy for our end use applications. My point continues to be that anything we can do to improve the efficiency of energy conversion is an important thing to do. So more efficient internal combustion engines, mechanical transmissions with lower losses, hybrid electric powertrains that improve on the efficiency of internal combustion engines. These are all things that we need to keep working on.
Thank you.
Finally, we're going to take one last question in case anybody wants to add something. Oh. Okay, we have a question from Zoom for you, Professor. I'm going to read it for you. The question is about the Ragone plot. It says this plot shows the most conventional way where it can compare between single options and a technology as a whole. This person would require clarification about how this Ragone plot is connected to the LCA results presented.
I think connecting Ragone plots to life cycle analysis is a very difficult thing to do. I think as a general idea, the Ragone plot is aimed at explaining how the specific energy relates to specific power in an energy storage system or material or device. So in this case, the Ragone plot is really focused on energy storage, and where you see fuel cells, we really mean gaseous hydrogen. Where you see IC engine, we really mean liquid hydrocarbon fuel, gasoline. So I think that the Ragone plot is a very specific thing. It just tells you what is the relationship between the ability to store energy and the ability to deliver power in an energy storage device.
Well, thank you so much. We are on time for the Ken seminar. Once again, we are very grateful with you for having given us this presentation that has been quite insightful about some numbers that I myself didn't know about. So thank you again, and we hope to have you in person in some other edition of the Ken seminar, Professor Rizzoni. Thank you so much.
It would be a pleasure. I'll make sure I visit your center next time I'm in Urbana-Champaign. Best wishes to all. Thank you for having me.
Thank you so much.
Thank you.